Hello, everyone. I'm so happy to be here today and to be presenting to you. And I'm going to talk about health monitoring using machine learning and wireless sensors. So, like many of you in the audience, I really came to health monitoring from wireless signals, from working on microwave. And in fact, over the last 10, 15 years, I have done a lot of work about how we can use advances in technologies in radios and signal processing to improve Wi-Fi, to improve cellular communications and wireless networks as a whole. But then just about, I think about five, 6 years ago, I started thinking that these wireless signals are really so powerful. And it's not just for connecting and making communication worse and sending messages. Of course, that's very important, and we have done so much in the last few decades on that front. But wireless signals actually can tell us a lot about the environment and other people and health also. So if you think of them, wireless signals spread in the environment, they traverse walls and occlusions, and they reflect off the human body. And if we can analyze these reflected signals, these signals that come from the environment to us, and then maybe we can start understanding and try to sense people that we cannot see, people that are occluded from us, for example, behind walls and obstacles. And maybe the next stage we can get something about their physiological signals, such as their breathing, heartbeat, etc. So when we started looking at this, I had some of my students and I was able to convince them that this is interesting and let's just look at it. And we started building our devices to try to sense people through walls. So I'm going to start by showing you one of our earlier results. So here you see our offices at MIT. You see my students standing in the middle of the room. And here is the first version of our device. And I'm going to put it in the office adjacent to where this guy is standing. So we are going to try to monitor him through walls and see whether we can monitor him using wireless signals and monitor his movements without any sensors on his body, purely based on those reflections. So the red dot that you see on the screen is where the device thinks that he's standing right now. So I'm going to play this video for you and look at the red dot and see how it's tracking him. So as you can see, we are able to track him pretty accurately. So you see the red dot is following him. And remember, all of this is just based on how his movement is changing the electromagnetic waves, and we are not having any sensors on his body or transmitters. So you can see we can track him pretty accurately. So this was, as I said, one of our earlier results. And we were very excited. We are able to track people and get their movements. And we kept working on this. And I want to show you some of our more recent results, particularly from last year at the end of 2018, at what we are able to do. But to understand what we were trying to do, like first, if you think about what I just showed you, that's very interesting. We can track him and track him very accurately. But if you think about it, one of the things that is still not here, we are not able to achieve it, is like, if you remember, like, so when he was walking, you can see that dot sliding, but you don't really know whether he stepped with his right foot, his left foot. You don't know that. And also, like you see him standing, you see that red dot in a particular location, so you know his location. But you don't actually know that he's standing or sitting there. So can we get that information? Can we, just purely by analyzing the wireless signals, get information that are richer than just location? So I'm going to show you our most recent result. And now I'm changing the view for you. So the bigger frame is actually what the device can see. And the small frame at the top is the camera inside the room. And remember, all of this we are able to see through walls and monitor through walls. And now let me play this video for you. Now you see that when he sits, you actually see a skeleton sitting. And you are seeing them as they are walking. You get multiple people, and you see advancement and like right foot versus left foot and all of that stuff. And remember, all of this just purely based on analyzing the reflected wireless signal through a wall. No sensors, of course, no cameras, nothing in the camera. It's just so that you would know the ground truth. So how can we do this? Of course, I don't have time to get into all of the details of how to do this. But at a high level, we use two important technologies, radios and machine learning. So we were lucky that over the last few years, there were so many advancements in radio and radio technology that we are able to use them to have very sensitive radios. So for people who are not in microwave, I tell them that if they want to think about the importance of the radio to our technology, the radio is like the ear of the device. You have these minute reflections of the human body that could potentially also have traverse walls and occlusions, and you really need very sensitive radios to be able to capture them and capture them accurately. But the real important part is really the machine learning, because the machine learning is like the brain, is the component that's interpreting these signals. So I'm not going to be able to get into a lot of the details, but let me just at a very, very high level tell you how this works. So when you transmit a wireless signal, I mean, we know that it can traverse walls and occlusions. It reflects off the human body because our bodies are full of water. And some of these minute reflections are going to come back to our device. So now at a high level, we can use something that we all learned from radar. So you know, for example, this very basic equation, radars can track object based on the reflected signals, and one of the most simple equation that you can use is that distance is equal to the reflection time multiplied by the speed of light. So we all know the speed of light, so if you can measure reflection time, you can potentially get the location of the moving object. So you can get that red dot that I showed you. Now, of course, this is too simplistic. It is simplistic for a variety of reasons. So, like if you think about the difference between what we are doing and what's traditionally done in radar systems, so apart from the fact that we cannot blast power, because I mean, if you blast power like radar, first of all, I mean, the FCC will be after you. Second, it's just not healthy. And we can't do that. But let's put power aside, that's not the biggest issue. The issue is that when you are talking about radar and you are talking about an empty, relatively empty sky, there are fewer reflections that you have to deal with. Now, if you are talking about an indoor scenario with furnitures and walls and so many reflections, we know that wireless signals not only reflect off the human body, it reflects off everything. The podium, the walls, the screen, the floor, the ceiling, everything. And in that cluttered multipass environment, you're not going to get one signal. You're going to get so many fictitious signals. In fact, it's even worse. You are going to get the signal, it comes, reflects off my body, and then reflects off the wall, and then of another body, and you get these multi-hop reflections, which create many fictitious signals. So we can't simply take these concepts from radar and apply them as is. Now, the second thing is I don't want just a dot that is moving. I want a full skeleton, as I showed you. And the human body is also a deformative body, as opposed to an object that is rigid, like an airplane. So while we are motivated by all of the wonderful technology underlying radar, we have to come with new innovations to be able to address this issue in indoor environment. So what do? We use neural networks. Now, neural networks are very good in the sense that they are able to capture and abstract a model. They can even abstract it, even if we as humans have no way of expressing it, they can learn it from data. So we are going to run neural networks and teach them how to interpret electromagnetic signals. Now, at a very high level, we are taking our electromagnetic signal, we are pushing it into a multi-layer neural network. Actually, our network is many more layers than this, and we spit out a physiological signal at the end. So it could be a skeleton like here, or I'm going to show you that we have other physiological signals later. And we train this neural network to be able to interpret the electromagnetic signal and transform it into the output of interest, like the skeleton. So I'm going to express just one important technical point here, although there are many, many components, of course, that we have to get right to be able to solve this problem. But one very important thing to notice is that when you are training a neural network, you are training it with some data. And you want to be able to take that neural network, and I showed you the skeleton that are moving, and to take it to a completely new environment, and it still works. You can't just take the device every place. You have to recollect data and retrain the device, and it doesn't generalize. That doesn't work. So how can we make a neural network that interprets wireless signals generalized to a new environment that it has not seen before? So think of it like we are training the neural networks with in Bob's home and Alice's home, and we want to generalize it so that it can detect these skeletons and the physiological signals in a new environment like Chris's home, for example. But we all know, so these are the source domains, and this is the target domain. So we want to generalize from the source domain to the target domains. We all know that wireless signals are impacted by the whole environment. So those wireless signals not only have information about the skeletons, but they have information about the closet and the walls and the bed and everything there. And if I have that information inside my network will not be able to generalize to a new place. So we have to train the network while at the same time eliminating the extraneous information that is irrelevant to the task. So how do we do this? How do we remove irrelevant information from neural networks? So again, at a very high level, think that you are taking your signal and you have a neural network that acts as an encoder to your signal. And the new representation from the encoder, you give it to a predictor, which predicts some metric of interest. It could be the skeleton in this case. Now, you want this representation, E of X, to be free from any environment-dependent information. That's what we want, so that we can take this network that we trained to a new environment and will be no problem. So how are we going to do it? So we are going to use a concept that is based, actually it comes from game theory, which is basically that we're going to train two neural networks. One of them is the predictor, and the other one is a discriminator. So these two networks are playing a game against each other. The predictor wants to create the skeletons, or the metric of interest. And the discriminator wants to know, by looking at the wireless signal, oh, this wireless signal came from Alice's bedroom, or from Bob's living room, or from Chris's kitchen. Now, if we can train, and during that training, during that game, eventually we make the discriminator lose, then eventually he will have no ability to distinguish, oh, this wireless signal came from this particular environment, because we have eliminated in our representation everything that is environment dependent, and we just left the information that is relevant to our task. And to do that, during training, we can have a loss function that is a combination of the loss of both the predictor and the discriminator. So it is the loss of the predictor minus some lambda value multiplied by the loss of the discriminator. And this goes on, this training goes on like a game, and eventually the discriminator will not be able to tell where the signal comes from, but the predictor is learning to predict at the same time and keeping that information. So this is a very, very high-level description of these neural networks. Now, I'm going to show you what we can do with them. So I showed you that we can get skeleton, but in fact, we can get other physiological signals about humans. So one interesting thing is sleep. So when I tell people that we can get sleep, they say, of course, I mean, I saw this video, so you can have this skeleton walk to the bed. You see them when they stop tossing around in the bed, when they step out. So you have a metric of sleep that's called actigraphy, space on motion. But that's not really all that is sleep. Sleep actually is much more than that, because when we are asleep, there are different sleep stages. So when you go to sleep, your brain waves change, and you enter different stages: awake, light sleep, deep sleep, and REM. And these sleep stages are very important. They are not just important for sleep. Actually, I mean, sleep on its own is very important. In fact, 1 in every 3 Americans have sleep problems. So if we can address sleep, that on its own is very important. But sleep stages are also important for a variety of diseases. Just to give you an example, think about depression. So in depression, one of the signs of depression is REM, the stage at the top, starts happening early on during sleep. And in fact, the big class of depression medications called SSRI, they are also known to be REM oppressant. So if you can monitor every night depression, if you can monitor REM or sleep stages, then perhaps you can detect when people are lapsing into depression and be able to address it. Now, okay, that's fine, but maybe there are other ways we can get these sleep stages accurately. So today, if you want to get sleep stages, you send your patient to the clinic. Actually, this is here in MGH Sleep Lab. And they put all of these sensors on their head and body, and they ask them to sleep like this. I'm sure many of the people in the audience have been to a sleep lab and went through this experience. As you can tell, it's not a happy experience from his face. It's very hard to sleep like this. And this is actually how we measure sleep today. It's really hard to imagine that this is representative in the first place. So let me show you how we can measure these sleep stages. So this is our device. It transmits very low power wireless signal, much lower power than Wi-Fi, analyzes this reflection using machine learning, and spits out the sleep stages throughout the night. So it would know, for example, when this person is in REM, which is the stage during which we dream. And as I said, we did this study with Mass General Hospital. We checked 25 subjects and more than 100 nights. And we trained our network, and we showed that we can get results that are comparable to the sleep lab. So in fact, to understand this result, let me just tell you a bit more about what happens in a sleep lab. So our accuracy is 80%. So is this 80% good or not? I have to tell you a bit more about what happens in a sleep lab. So when you go to a sleep lab and they put all of these sensors on your head and body and ask you to sleep like that, in the morning, there is a sleep technician who comes and looks at your signal. And for every 30 seconds, that sleep technician has to put a label: light sleep, deep sleep, REM, etc. Now, if you take the same exact signal from the same person on the same night, give it to a different sleep technician, and that person starts labeling, the consistency between 2 sleep technicians on the same data is about 83% on average. So being able to get an accuracy that is 80% without any sensors on the body and in the person on home and every night, that's very much an improvement, and the accuracy is more or less comparable to the consistency between 2 different scorers, 2 different sleep technicians. Now, what else can we get? What other physiological signals? So this person is sitting like you guys, he's reading, and what you see on the screen is nothing but his inhales, exhales. We ask him to hold his breath, and you see the signal stays at a steady level. He has no sensors, nothing on his body. It's completely contactless by analyzing the wireless signal. We get his breathing. And we know that this is the correct breathing, not just because we look at it and say, oh, can you hold your breath? It's actually because we have done extensive studies where we put FDA-approved chest band on the people and compare the signal that we get to the actual breathing signal that you get from FDA-approved devices. Now, I want to zoom in on the signal. So this is the same breathing signal that I showed you before. These are the inhales, these are the exhales, and there are blips that you see on the signal. These blips, they are not noise. They are his heartbeats. And of course, we have separate algorithms that can disentangle the breathing from the heartbeat so that we can get both vital signs. So what kind of application can you have with such a device? So, of course, there are many potential applications. So there are applications in smart homes where you can see how people are moving around and we can activate and deactivate devices. There are applications in security and many others. But the application that me and my students were particularly and are still very, very excited about is healthcare. So when we started publishing our results, we had many doctors coming to us and saying, can you monitor my patients? I would like to get objective information about how they are doing. And of course, you can see like we are monitoring many of these physiological signals, but to be able to appreciate why actually this is very important in healthcare, think about the situation in the US. So the cost of healthcare is over $3 trillion. Most of that cost, it comes actually from chronic diseases. So we know that medicine has improved a lot, but actually as a result, a good result, people are living longer. But with older age, you get all of these chronic diseases. And many people, actually in the US alone, there are 13 million seniors who live alone at home with chronic diseases. And the problem with chronic diseases is that actually they are very costly. Those people live alone and they are older, so they might not feel like going to reach to the doctor. Sometimes they think, oh, this is just an age problem. But interestingly, many of these diseases, what happens is that problems don't happen overnight. Like when somebody gets exacerbation in heart failure exacerbation or COPD exacerbation, they build up gradually. So if you can continuously monitor chronic disease patients in their homes, you can potentially detect degradation in health early on and have the doctor intervene before the patient ends up in the hospital. That would be much better for the patient, much better for the whole healthcare system. But how can you monitor patients today? So let me show you the picture of what you can do today without our device. So if you want to monitor something like a breathing signal, you either have to have a nasal probe, like the guy on the top, or you have a chest band on the person. And they have to wear it and live like that. So if you want to monitor sleep, as I showed you, you have to have these like sensors on the person's body and head, like the woman in the bottom. In diseases like Parkinson's, multiple sclerosis, where you want to monitor motion, you put these accelerometers on people's limbs. I mean, this is not how people are going to live continuously their lives. This is not something, I mean, try to convince grandpa or grandma to wear these kind of devices continuously. So what's good and what we are able to do is to transform this image and remove all of those sensors. So we can monitor all of these things and many more things just without anything, without asking people to wear sensors or change their behavior in any way. So what we have a wireless device that from the use perspective, you can think of it as like a customized, smarter box that looks like the Wi-Fi box, sits in the background of the home and uses the electromagnetic signals in the environment to analyze and monitor breathing, heartbeat, gait, mobility, falls, interaction with caregiver, and sleep stages, apnea, and many other things without a single sensor on the patient body. Just people can live their lives, and the device will be able to tell all of these vital signs and be able to detect changes in them. We call it the Emerald wireless box. So over the last 18 months, we have been working with hospitals, with medical doctors, with pharmaceutical companies in multiple diseases, and we have deployed our devices in more than 200 homes. And in particular, we have worked with patients that have Parkinson's disease, patients that have Alzheimer's, patients that have COPD, and patients that have depression. And I want to show you some of the results with actual patients. So what I showed you earlier are results from the lab with healthy students. So now let's just see from actual deployments with patients. Okay, so let's start with something simple. And here I'm going to go back, I'm just going to show you a dot moving as opposed to a full skeleton, because even just using the dot, not the full skeleton, is so powerful in understanding health. So this is an experiment that you're going to see the difference between how a patient, an elderly patient, walks and how a healthy nurse walks. So this patient lives in an assisted living community. And what you see, there is a green line at the top, green rectangle. This is our device, the Emerald device. And the red dot is the patient, or like on one of them is the patient, the other one is the healthy nurse. Let me play this video for you. So look at the patient and how he moves versus how the nurse moves. So of course you can see that the nurse moves faster than the patient. I mean, she's healthy and younger, so she moves faster. But the other thing that you notice is that the trace that she leaves is smoother than the patient. You see that the patient, his movement is wiggly. He has balance issues. Now this is quite important because balance issues can lead to a fall, which actually can lead to a major problem for the patient and injuries. Now, let me show you some of the results from a study that we did with the Michael J. Fox Foundation in Parkinson patients. So here, again, you see the unit, the residential unit, F1 patient who has Parkinson's. And you see the device, the rectangle box at the top. This is, again, another patient who also lives in an assisted living community. And this blue line that you see is a 2-hour trajectory from this patient. And you see that the trajectory goes between the bed, there is a chair, there is a bathroom, and also this cabinet that you see there, actually this is a kitchen area so that the person can cook some food. So we take these trajectories and we abstract them and try to understand the life of this patient. So let me explain this graph for you. So this graph is from the patient in this scenario. So this person is a Parkinson patient, and we collected all of these trajectories, and this is generated this graph. So this graph spans 8 weeks. Every single circle in this graph is 1 day. So the 0 is midnight, and 12 at the bottom is noontime. So every circle is 1 day. The innermost circle is the first day of the experiment, and the outermost circle is the last day of the experiment. So I want you to look at the blue color first. And blue really refers to the time when the patient is in the bed sleeping. So if you look at the inner circle and you look at the blue next to the center of this graph, so these are the first week of this experiment, you see that the blue is very fragmented. So this person is not having good sleep. His sleep is very fragmented. As this study goes on, you see that the blue starts being consolidated. So his sleep is improving significantly in the outer circles. Now also, you see that the whole graph is full of green color. Green is the time when he's sitting on his chair. So if I go back here, and you see that chair where you see there is a blue trajectory on the chair. This is his favorite chair. He spends most of his time sitting on this chair. So when he's sitting on the chair, you see that green color. And this immediately tells you that this person is spending most of his life just sitting on a chair. I mean, apart from the fact that this is really not the most exciting life, but also this is very worrisome for his health. Because when people are sedentary, particularly at older age, that creates so many health problems. And his doctor would like to know that and try to do something to make him more mobile. I want you also to look at the yellow color. So yellow is bathroom. And you see a cone of yellow around 8 a.m. Between 6 and 9, there is a cone of yellow. So around 8 a.m., we are seeing that he's doing his toileting and he's dressing. So he's going to the bathroom around 8 a.m. Now, if you look at this graph, you should be surprised at the beginning, because if you think of it, the blue stops around 3, 4 a.m. So he wakes up around 3, 4 a.m., but he does his toileting and dressing around 8 a.m. Sits on a chair, waiting until around 8 a.m. to do his toileting and dressing. Can you guess why? Exactly. This is a person who lives in an assisted living community. And he's waiting for the nurse or the health worker to come and help him to do his dressing and toileting. He's so dependent on his caregiver, he can't even do his toileting on his own. That's very important information because when people are very dependent on the caregiver, they are more fragile. You have to make sure that they are living in an environment where they have their caregiver and their caregiver is available. Another thing that you can see here is white regions. So white is when the person is outside the coverage area of the wireless signal. So with our device, we can monitor his unit, and we told the device not to monitor other units, and also because of the wireless coverage, we are limited to his unit. So when you see white, it means that he's outside his own unit in that assisted living community. Now, if you look at around 6 p.m., 18 is 6 p.m. in the afternoon, you see a white cone, okay? So this is because he goes out every evening and have dinner with the rest of the people in the assisted living community, and that dinner happens to be around 6 p.m. So every single day, he's really very much into this ritual of having dinner with the rest of the people in the assisted living community, except actually for one day, if you look very carefully, you see the green line and a few colors there connected. So he didn't feel well, he came back early. So, I mean, if you think about it, like when the doctor sees a patient, what do they ask them? They ask them about how's your sleep? Like, are you, like, how is your toileting behavior? I mean, do you wake up, go to the bathroom? How often do you go to the bathroom? Do you feel that you are mobile or that you are not able to move as much as you were used to be before? Kind of like all of these information, but even me, and I cannot remember really if you ask me how good my sleep over the last, I don't know, few days. So being able to, and actually it's widely known that if you ask people about their sleep, they have very, very distorted perspective. Sometimes it takes them, I don't know, 12 minutes to fall asleep. They tell you it took me 1 hour. So now you have very objective information, and without even asking people to change their behavior, write diaries, or do anything, to just live your life. So these are 6 Parkinson patients, and I'm now going to just focus on sleep. And you can see here that although all of these 6 patients are Parkinson patients, their sleep behavior is very different from each other. So you look at this person here, and you see that they go to sleep around, like the bottom guy here, goes to sleep around 11 p.m. and then wakes up around 6 a.m., like many of us, reasonably normal sleep. Look at this other person at the bottom here. The sleep is all over the place. I mean, it's really hardly like he's sleeping in any normal way. And you would be wondering, how can he live like that? And these are all Parkinson patients. And in Parkinson, actually sleep is known to be a very big problem, but also it is treatable. So being able to know how bad or good someone's sleep is, the doctor can intervene and help them. Here is another aspect, which is the impact of medications. So what I'm plotting for you here on this graph, on the x-axis is the hour of the day, and on the y-axis is the gait speed of the person. And this person has Parkinson's. Now, if you look at this graph, first, every single point, every single dot is the average over 2 weeks period. So when you see a dot around 2 a.m., it doesn't mean that this person wakes up every night around 2 a.m., but it means over that 2-week period, whenever he was awake or walking between 2 to 3 a.m., we got some measurements and then we averaged them to create that dot. Now, look at this graph. What is the first thing that comes to mind? It's like there is an inflection point. What's going on here around 5 a.m. while suddenly he actually walks better? It turned out that this is exactly the time he takes his medications. So, I mean, you probably know and have seen some Parkinson patients. So Parkinson affects your ability to walk and move. And when the patient takes his medications, the tremor and all of those symptoms are much better, and he's able to move in a much smoother way. But what is really interesting about this graph is not just that this is when he takes his medications. What's really interesting from a doctor's perspective is that when you have Parkinson patients, actually every patient is different. Every patient is just his own disease to a large extent. And today, the doctor does not know what is the right dose for Mr. Smith. So he just say, okay, we're gonna, like, you are stage 3, we're gonna try this particular dose. Let me know what happens if we need to increase the dose or not. But here you can see, actually this patient is very well managed because he takes his medication, and you can see throughout the day, he's kind of stable. And then at the end of the day, the gait speed goes down. So he's very well managed to sustain good performance throughout the day. And then during nighttime, it's okay that the medications is wearing off. So being able to look at this information, the doctor can adjust the dose for each individual patient. Now, you might be saying, but how do I know for sure that this is actually related to medications? So on one hand, we know that this is the time he takes his medication by asking the doctor and the nurses. On the other hand, we do what is typically done in medical studies, which is to compare to a control subject. And in this case, we use his spouse as a control subject. So she lives in the same environment. She doesn't have Parkinson's, so you can see her gait speed is she can walk much faster than he can because she doesn't have Parkinson's. But most importantly, you see that there is no inflection point. There is kind of like a steady speed around which there is some randomness. So I want to also show you that the device is able to capture breathing abnormalities. So I showed you my student who's healthy, and he was holding his breath. You saw his breathing. So how about sleep apnea? So we know that sleep apnea is widely common, and it's not diagnosed in many cases. So here, let me show you an instance with our device capturing sleep apnea. So here you see the breathing of a patient. And see, like, he breathes, inhales, exhales, and then suddenly he stops breathing. This is an apnea event. And then again, you see him breathing, and then again stops breathing, apnea, and again and again. In fact, when we monitor this person, he also lives in an assisted living community. The nurses came and say, this person wanders around at night. Can you actually monitor his motion so that we would know when he starts wandering around? And then we monitored him. We discovered that he has sleep apnea. So it's very hard to actually sleep the full night. So he wakes up because of the apnea and starts not being able to go back to sleep, wandering. But the problem is the apnea, is not the wandering. It took them about 8 months to send this person to an actual sleep lab to put all of this stuff on him, and they told them exactly the same story. He has severe sleep apnea. Okay? So I want to end by showing you finally some of the results from the skeleton base. So here I'm going to show you that the person can walk behind walls, and we can get their skeleton. You can see that we can do multiple people, and this is, again, another person getting behind the wall, and we are able to continuously monitor them and getting skeleton from behind the wall. Here you see multiple people with different types of occlusion, so it's not just wall. It can be furniture and different types of occlusion, as long as the wireless signal does not get attenuated too much. And of course, as opposed to a camera, I mean, wireless signals can see through darkness and occlusion, so you can also see those people despite that you can't see them through the camera. And you can see them, it's not just walking or moving here, like one person is sitting, the other person is like trying to describe something on the board, and as the person stands, you see all of that. And Also, you saw different environments. This is yet one more environment from MIT. People are getting downstairs, upstairs. So I want to end with 2 points. The first point is that, of course, what I presented to you is a powerful technology. It can see people through walls and get their vital signs without any sensors on their body. Now, because of this power, this power enables us to do so many things, but also this power is something that we have to consider very carefully because of all issues related to privacy and security. So we have to be very careful as we use this technology to maintain the privacy of people and to ensure that their health information and other personal information also is secure and does not end up in being accessible to the wrong people. And one of the nice things about working in the healthcare domain is that the information is, you have to be very careful, and there are protocols to do that. So you can't just go ahead and run a study with people. You have actually to write ahead of time a protocol, what the study has to be, what exactly you are monitoring. You have consent forms that have to go through an IRB to be approved to do that study, and you have to present those consent forms to the patient, tell them exactly what you monitor, and they have to consent to it. So, and that actually is very good, I think, for this kind of technology being in the healthcare domain, so that we are very careful about privacy, about the use of the technology in the right way. The second thing, of course, is from a technology point of view. So we separate completely. We don't store any information about people's names or age or anything like that. We only store the measurement. We encrypt it, separate, and anonymize the measurements so that the link between them and the actual person has to go through multiple hubs that are all encrypted. And in fact, it's not even stored in our system. The third thing that is important is that when we monitor somebody, we only monitor what is needed and what they consented to. So for example, if somebody only has sleep problem, you don't have to monitor their skeleton and how they are moving. While if somebody has like Parkinson, it is very important to monitor their movement and their tremor, and then you monitor that, but they know that you are monitoring it. So you don't have to monitor everything. Every one of these things actually is a separate machine learning module, and you can completely deactivate it depending on the study. And of course, at the end of the day, the patient is the one who owns the data and can decide what to do with it. So I want to end by just conveying to you how much I'm excited about the integration of these two disciplines together. So healthcare is very important. Actually, it touches all of us. And then all of us here in this room, we come from the fields that are related to microwave, to wireless sensors, to wireless communications, to signal processing. And seeing those two fields coming together, and with the advancement of machine learning, being able to do something and change healthcare, I think is very, very exciting. And it is important because actually, without introducing innovations to healthcare, the current system is not sustainable. Just with the aging population, with the baby boomers now reaching a retirement age, we really need to do something about it. And technology can help as long as we are innovative, but also very careful about how we use the technology. Thank you.